Hello, everyone. I am Zhenhua Wang from NUDT. It is my pleasure to share our research with you. The topic is about understanding the XXE vulnerability via automatic analysis. My presentation contains 3 parts. First is the motivation and challenge of our research. Then, I will introduce our solution, a framework called XHunter, which automatically discover and rank XXE vulnerabilities. Finally, I will provide the experiment evaluation, and summarize the contribution. Extensible Markup Language, XML, plays a significant role in web applications. It is very useful for developers who want to process a document's contents without tag limitations. Its self-defined architecture allows XML to provide highly readable context information and to support data assessment and aggregation. These characteristics have led to the wide use of XML, and many projects have adopted it. It is used for configuration files, document formats, image headers and network protocols. Its application is so common that any problems with it could have catastrophic results. The flexible nature of XML poses security risks. Inappropriate entity resolution may lead to several vulnerabilities. OWASP listed the 10 most serious web application security risks, and XXE ranked 4th. We first need to understand the structure of XML, which consists of 3 parts: an XML declaration, a document type definition, DTD, and document elements. The DTD defines the attributes of the elements and entities in XML documents. It is worth noting that entities can be declared in XML documents or introduced from outside. An external entity is designed for creating shared public references between multiple documents. However, this means that the entity will obtain content from external sources. Attackers could leverage this feature to access internal sensitive data. The external XML entity, XXE, attack was first put forward by Stuck. Later, researchers proposed more advanced attack methods, such as out-of-bound (OOB) attacks, schema entity attacks and billion laugh attacks. These attacks can lead to denial of service (DOS), the leakage of sensitive information, and forged server-side requests. With the generalized use of XML in web applications, XXE attacks have also become widespread. Many famous applications have been found to have XXE vulnerabilities, such as Google, Facebook, WebSphere and WeChat Pay. Our research aims to find XXE vulnerabilities in the latest popular web applications. There are 3 main challenges. The first is complex structure. Modern web applications have thousands or even millions of lines of code, and contain a number of functional modules. It is challenging to draw call graphs for all the code, as the time and space consumption will be unacceptable. Moreover, model, view and controller (MVC) is a popular design pattern in web applications that separates the data processing, model, and business logic, control, from the presentation, view. This design facilitates the modular development of applications but also brings great difficulty for code analysis. The second is complex logic. Most functions are implemented based on classes and methods. This feature makes a program modular but also brings great complexity to the logic. The calling relationship between methods is very complicated. A method may be called by other methods in the same or different classes, with multiple files between them. The inheritance of classes and the rewriting of methods make the analysis more complicated. This means part of the code is implicitly included in methods. Moreover, implicit inclusion relationships are also common in complex PHP programs. For example, the namespace is used to clarify the use scope of classes and functions. Therefore, we need to analyze the namespace to determine the function currently called. The third is sink reachability. After discovering a sink, we need to know whether the sink can be accessed. The method and possibility of exploitation vary for different sinks. Some sinks are located in a general parse function, which may be invoked in follow-up development. In some scenarios, Local configuration files are parsed in XML format, which can be exploited with file upload vulnerabilities. Some applications parse API response data for processing orders, obtaining weather or map information. If the response data contain malicious elements, attackers could compromise the web system. Sometimes, the parsed content is pieced together, which makes it difficult to launch attacks. Therefore, we need to judge the reachability of a sink and give a risk level for it. Our goal is to build a precise and efficient framework for XXE vulnerability detection and ranking. We need to consider the structural complexity of modern web applications, which stem from object-oriented and MVC design. To tackle the challenges mentioned above, we divide our approach into 3 parts. 1. Vulnerabilities verification. 2. Call chain analysis, and 3. Vulnerability ranking. First, we find vulnerable sinks. As the files related to XML operations account for a minority of the total, we adopt program slicing to find the related files. Then, we build abstract syntax trees, AST, for the target files. We locate the sensitive function, method, call in AST node. Starting from these sinks, we build control flow graph, CFG, to identify the source of critical variables. In the interprocedural pointer analysis, we build the call chain through multiple rounds of vulnerable function updates. Starting from the sink, we look for the caller of the current function or method. Once it is found, a new node is added to the call chain, and XHunter updates the current vulnerable functions. This loop will end when no new caller can be found. We can rank sinks according their call chain. We set 4 levels, corresponding to different code scenarios. If the last node is accessible to the user, a high-level vulnerability is found. Moreover, lower-level vulnerabilities are also worthy of attention. The level judgment mainly focuses on the source of the parsed data and the application scenario of the vulnerable function. We mainly use the 2 following steps to verify vulnerabilities more quickly and accurately. 1. Sinks discovery, and 2. Interprocedural analysis. As a small percentage of files are involved in XML data processing, we filter out the files with vulnerable functions. This method sharply reduces the analysis complexity. To discover sinks, we build an abstract syntax tree for the target files. Through this, we can determine the properties of each statement. Starting from the first statement, we recursively scan each node and find the function call node of security critical functions. After finding sinks, we do taint analysis for sensitive variables of vulnerable functions. If the sensitive variable points to user input or function parameters, its enclosed function will be marked. For the call graph, we do not build it for all functions, but only for the identified sink node. If a new sensitive function is found, we record a node, which contains the name of the function, method, class and file, the vulnerable parameter's location, and its calling function. In XHunter, we propose a demand-driven backward data flow analysis method. We start the search from sinks and work backwards to find the affected function, method. In each round, we update the list of current vulnerable functions. This process loops for many rounds until no new vulnerable functions are found. Finally, we obtain the call chain of the affected function. This approach greatly reduces the time and storage space consumption. As an example, the call chain of our real-world example is shown in figure. We can see that this call chain contains 5 functions from the XXE sink to the user reachable function. The reachability of different sinks varies. To determine the damage of a vulnerability, we design an evaluation standard for risk level judgment. With this standard, we can rate vulnerabilities automatically. The user can trigger the sink directly, which could lead to severe XXE vulnerabilities. It is worth noting that some functions can be accessed from the outside under the routing control of the CMS, which is also accessible. In call chain analysis, if the last node is user accessible, this vulnerability is considered high risk. In this case, the sinks are found in general parser functions. The developer may use them in the secondary development process, which could trigger an XXE vulnerability. The call chain may contain only one node, but the function is general purpose. These functions parse response XML data from APIs, such as pay, map, and weather information. These data are difficult to control unless the official site is compromised and modified. Attackers could also launch domain name system (DNS) attacks, which direct requests to the attacker's site and control the XML content. The last node of the call chain can be triggered by the attacker, but the data are from the network. These functions deal with local XML files or concatenated strings, which are difficult to exploit. Only with other vulnerabilities, such as unrestricted file upload or database injection, could this lead to an XML injection attack, but it still deserves our attention. After all, the security of the system depends on its weakest part. We evaluated XHunter on 22 real-world PHP applications, as shown in Table 1. Our target applications were gathered from highly rated CMS projects on GitHub and popular CMS applications listed by W3 Techs, such as Joomla, Drupal, and Shopware. We selected web applications on the basis of 3 criteria. 1. The application is open source, and the latest version can be downloaded. 2. The software are popular and influential, e.g., has more than 1K stars on GitHub or more than 10K downloads. 3. They are modern multi-tier web applications with complex logic. XHunter was deployed on Ubuntu 20.04 LTS VM with 8 2.3 GHz cores and 16 GB memory. We first downloaded the program code and deployed the vulnerable applications. This process included installing the applications with database initialization and creating an administrator account. Then, we found the exploit paths through XHunter. Finally, we leveraged basic XXE payloads to confirm the existence of the vulnerabilities. After manual confirmation, we responsibly reported the vulnerabilities to the vendors. We summarize the results of the experiment. XHunter constructed a total of 307 sinks and 193 nodes. On the evaluation set, XHunter could find call chains that contained 6 nodes at most. We gave different security ranks for the sinks, among which 15 were high-level, 58 were medium-level, 85 were low-level, and 99 were minimal-level. In each round, we identified vulnerable functions and recorded their information in a node, which contains the name of the function, method, class and file, vulnerable parameter location, and calling function. We recorded the number of nodes generated during the analysis of each application. In preprocessing, we selected files containing vulnerable functions to reduce the complexity of analysis. In the first round, we examined calls to XML parsing function as sinks for XXE vulnerability. If new vulnerable functions were found, they were used to check the files in the next round. After program slicing, we sharply reduced the number of files to be analyzed. Table 2 shows the results of program slicing. Each CMS corresponds to a set of numbers. The numbers in parentheses are the number of all files, and the numbers outside the parentheses are the number of files selected after slicing. On average, only 2.79% of the files are needed to be analyzed. The false positives are mainly caused by 2 reasons and could be pruned in our future research. 1. Prohibiting loading entities. The programmer could disable the XML parsing. In this case, the XXE vulnerability cannot be triggered. 2. Filtering user inputs. In some scenes, the XML parser needs to load external entities. The developer filters some keywords to stop attackers. Among the vulnerabilities, 5.8% are high-level, which allows attackers to trigger the XXE vulnerability directly. 22.6% are medium-level, and they can lead to security events only when dealing with malicious XML files. For example, in module PHP Excel, XML files are parsed without sanitation before version 1.8.0. 33.1% are low-level, as only with extra vulnerabilities could we launch the next attack. At last, 38.5% are minimal level, whose trigger conditions are very harsh. We responsibly reported the details of the vulnerabilities to vendors. Some security groups replied quickly, while others did not consider the reports seriously. Table 5 shows the results of our reports, some of which have received a CVE ID. However, some vendors rejected or ignored our issues due to insufficient security concerns. As shown above, XXE vulnerabilities give the attacker opportunities to control the site. We strongly recommend that security vendors fix the reported security issues. However, some vendors do not provide ways to push issues. Not all high-risk vulnerabilities are listed below. These vulnerabilities pose a significant threat to web application security and may lead to several attacks. Disabling entity resolution is an easy way to patch them. However, for situations that need to resolve entities, we need to establish more fine-grained security protection strategies. In conclusion, our main contribution is proposing XHunter and making a large-scale analysis of popular web applications. XHunter implements interprocedural, object-oriented call analysis for modern complex web applications and rates the vulnerabilities. We use XHunter on 22 popular open-source applications, including 55.8 thousand PHP files and 9.2 million single lines of code. We locate 193 vulnerable function nodes, and 257 XXE vulnerability sinks are found, among which users can directly access 15 high-risk sinks. It is worth mentioning that XHunter is the first reported work that builds exploits and ranks for XXE vulnerabilities. My presentation is over. If you want to know more about our research, you can either read the full paper or email me. Thanks for your listening.